Today, we're going to be talking about confounding variables and why we need experimentation. Now, as a data scientist or an economist across industries, you are often going to be asked the question, what is the impact of something? For example, if you are working in public policy, you may want to know the incremental impact of a college degree on future wages. If you are working in public health, you may want to estimate the impact of smoking on your life expectancy. And these same questions are also very popular in the tech world, for example, in sales and marketing or on product teams. So we might ask, what is the incremental impact of advertising intensity on user retention? So if someone sees advertisements more and more frequently, how does that affect their likelihood of coming back to the site? Also, if we are a business to business SaaS company, we might ask, what is the incremental impact of being assigned a dedicated account manager on revenue as opposed to letting the account self service? Now, there's an important reason that companies need data scientists or economists to solve these types of problems. And that is because simple comparisons between groups that have a treatment and don't have a treatment tend to be biased. So let's say you're working for a large social media company and you want to know how many ads you can put in their newsfeed. We might want to know what the impact is of having a high or low ad frequency on user retention. But what if we just simply compared users who were fed a lot of ads versus users who were fed a small number of ads? If those ads were shown at regular intervals, then the longer you use the site, the more ads you received, right? That means users who have a high affinity for using this website use the site the longest, and users who have a high affinity for the website are also going to be most likely to return. Why? Because they like using the product, they like using the website. But because those users are on the site the longest, that specifically means that they are going to receive the highest number of ads. And therefore, the users with a high number of ads are also going to be those same users that are most likely to return. But do we really believe that users receiving more ads causes users to be more likely to return? Probably not, right? So what's going on? Why is it that users who receive the most ads are also going to be the users that are most likely to return to the site? Well, affinity for the website or affinity for the product, this is how much you like the product, how much you like the site, all else equal, is a confounding variable. A confounding variable, by definition, is unobserved, so we cannot directly measure a user's affinity for the site, or it's difficult to measure, right? We might have proxies for how much a user likes it, but we can't just measure it and quantify like this person likes it 3,000. The confounding variable is also correlated with both the outcome. So if you have high affinity for the site, you're likely to have high return rates, but it's also going to be correlated with the independent predictor variable. So in this case, high affinity for the site means high usage, which also means high ads are shown. And so if you go back to the business question, we want to know is how much does seeing a high number of ads compared to a user that receives a low number of ads, how much does that change their likelihood of returning to the site? But if we simply compare those with a high number of ads to those to a low number of ads, in effect, we're actually comparing users with a high affinity for the site versus users with a low affinity for site. So we're not going to be able to isolate the impact of just receiving ads. So how do we estimate the impact of various treatments when we have confounding variables? So the answer is randomized experiments. Now, there will certainly be complications and obstacles to doing experimentation down the line, but in general, when you hear what's the impact of something, your mind should first thought at least go to experimentation. And that's because with a sufficiently large sample size, randomization ensures that the treated and control groups, so in this example, users that are fed high ads versus users that receive low ads, if they are randomized into those groups, will not only be equal in expectation on the observed characteristics, anything that we can measure, but they will also be equal in expectation on unobserved characteristics, such as your affinity for a website or a brand. So when we look at users who receive the treatment versus users who don't, when they're randomized in sufficiently large quantities, then the difference between these groups is only going to be the treatment itself and not any other underlying differences between them. Now, be careful because this can fail in small samples. So let's say you are randomizing states, there's a sufficiently large probability to be concerning that, say, Texas, California, and New York all end up in the same treatment or control group. Now, in the